Good afternoon. Welcome to Exploiting Qualcomm WLAN and Modem over the air in Lagoon GHI with Xiling, Gong, and Peter P. Before we begin, a few brief notes. Stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline Ballrooms on Level 2. The Black Hat Arsenal is in the business hall on Level 2. Lunch is in Bayside AB from 1 to 2:30. Don't forget the merchandise store on Level 2 and session recordings from SOK. They have a desk on every level. Thanks for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for the voicemail to pick up. Please use the microphones in the aisles for any questions following the talk. And with that, let us welcome our speakers.
Thank you very much for attending our talk. In this talk, we'll share how we exploit Qualcomm WLAN and Modem over the air. And finally, we comprise the Linux kernel. About us, we are security researchers, both from Tencent Blade team. Tencent Blade team is founded by Tencent Security Platform Department in 2017. We focus on security research in the areas of AIoT, mobile devices, cloud visualization, blockchain, etc. This is the agenda. First, we will introduce some related work. WLAN security is a hot topic in recent years. The lone exploit on Broadcom Wi-Fi chip is on 2017, and this year on Marvel. Today, our talk is about Qualcomm. As we know, there is no public exploit on Qualcomm Wi-Fi chip. So how about the Qualcomm Wi-Fi? There is a simple illustration about the architecture of Qualcomm Wi-Fi. There are two important things. The first one is that start from Snapdragon 835. The WLAN firmware is integrated into the baseband subsystem. The WLAN and modem firmware are run in the same processors now. The second thing is that you can see in Qualcomm's implementation, most of the function is implemented in the Linux kernel driver named QC-ACLD. There are plenty of vulnerabilities in this driver. That is the well-known WLAN host vulnerabilities. Our talk is not about the WLAN host issues. It is about the WLAN firmware itself. There is no public talk on the Qualcomm WLAN firmware previously. So how about the security status? We will answer this question. Before we go into the details of WLAN and the modem firmware, we need to introduce the debugger we use to debug the firmware. This is the key step for us to analyze the modem and WLAN firmware. You can see there are MBA and the modem images in file system. MBA.mbn is the MBA image. Modem.mdt and modem.bxx are modem images. These images have a specific format according to Qualcomm's official document. Like application processor, modem processor also has its secure boot flow. The flow is like this. Firstly, Linux kernel will load MBA and modem images from file system to physical memory. And the second, Linux kernel will set the start physical address of MBA and reset modem processor. Then the modem PBL in the ROM will verify the MBA image. If success, it will jump to the MBA code. Finally, MBA will read and verify modem images. If success, it will jump to the modem main code. The pure boot function in Linux kernel describes the boot flow of a modem. It will load MBA.mbn and modem images to physical memory, then trigger MBA and modem images to be verified and executed in the modem processor. Linux kernel can restart the modem processor at any time. It will hit this function, pure boot, each time when restarted. The vulnerability we use to bypass the modem secure boot is a time of check, time of use bug. When MBA verifying modem images, it doesn't lock the physical address region. It means that Linux kernel can still modify the modem images. So after MBA verified one image, Linux kernel can modify it, which means we have bypassed the secure boot check. The bug POC is quite simple. There is the diff file of pure boot function. We just change the pure boot function. We let the pure reclaim mem function after we have modified the modem images. After we have ability to modify the modem images, we can inject debug server to modem side. We injected demonstrate to wait for commands from Linux side. The commands and the results will be exchanged using shared physical memory. So we can issue debug commands to debug WLAN and the modem firmware because they are in both modem processors. Now we have the debugger. We can analyze the modem and WLAN much easier. So Xiling will introduce the following details.
Okay. So I'll introduce the reverse engineering and the vulnerability and exploitation. And then finally, we'll explore it into the Linux kernel. Okay. Let's go. Let's review the architecture of Qualcomm WLAN. The WLAN is now in the baseband and the hexagon architecture, so that we can analyze the WLAN, and if we control the WLAN, we will control the baseband subsystem. Okay. Here is a simple figure for the WLAN architecture, and from the figure we can see that the Qualcomm WLAN firmware is not the full format firmware. Most of the functions of WLAN are implemented in the Linux driver. Here, the QCACLD, and the firmware itself is quite simple and just leading to a smaller attack surface. The work to be done in the firmware is called offload. Offload. The major attack surface, I think, is in the offload handler. It's here in the offload handler, the non-data offload handler, and the data handler. And the offload handler will inspect the OTA packet, and if interested in, will pass the packet and do some job accordingly. So the attack could happen here when the offload handler passes the packet. The offload handler is in fact a table with some different handlers according to the status of the Wi-Fi. Okay. Give an example for how a Wi-Fi access pointer is displayed on the Wi-Fi list. When you open the Wi-Fi on the UI, the Android framework will issue command to the driver, and the driver will command the firmware to scan the nearby Wi-Fi hotspot. Finally, the WLAN firmware will register the handlers into the offload handler table. You can see into this table. And when other access pointer or hotspot send a package, the handler will receive and pass the incoming packet. And if the packet is a management beacon, the firmware will forward it to the Linux, and the driver will pass the packet and extract the SSID and notify the user space application. And finally, you'll see the Wi-Fi point hotspot is displayed here. Okay. Okay. So now we have some basic things about the WLAN. Let's start with reverse engineering. The firmware is located here and loaded by the modem. Okay, so this file, you can find it from the phone. And here is the disassembler. And Qualcomm provides us the wonderful SDK and the instruction reference here, if you are interested in. Okay. The WLAN firmware has about 8,000 functions. It's a difficult task to reverse these functions without any knowledge. Luckily, Qualcomm has given us some hints. The most useful thing is that the string table. With the string table, we can find a lot of useful function names. And another important thing is the import function here, because the WLAN firmware is loaded by the modem as a shared library. So the WLAN is using a lot of functions from the modem and leave the function name in the import function table. That's quite useful. Okay. The target we are going to reverse engineering is the offload handler. It's the module tag surface over the air. The main question is, how can we find the offload handler? The answer is that you can first find the string from the string table. That is the long data offload, and then check the reference of the string to find the function named long data handler. And this function is actually a very big loop. It will fetch each item from the table and call the handler. Okay. Each handler is a function. This loop will call it from the table. Here is a sample of the outflow handler in the table. The key to reverse is to find the data pointer. From the figure, we can see that it's quite simple. The data pointer is a pointer combined by the 4 bytes, 58, 59, 58, 50B. This is the packet data over the air. If you send the data packet using the Wi-Fi dongle or other device, you'll find that your data is here in this pointer. So every offload handler has the same structures. I think this is the most important slide in this talk. With the sample offload handler, you can just simply walk through all the other handlers and analyze how the handler processes the packet and handle vulnerabilities. Yes, this is the most important slide, I think, in this talk. The data pointer here, okay. You can see here this data pointer, and we fetch 1 byte from the data and test the C, test and C. From the specification of WLAN, we know we test this byte means test whether this packet is a management beacon. Okay, so now we can start the exploitation. This is the overall roadmap. We are here now. We have controlled Wi-Fi dongle or something else could send out Wi-Fi signal. We are going to compromise the WLAN. Yes, this is over the air, and then we are escape into modem, and finally we are get into the Linux kernel to complete the full exploit chain. Okay. Before we go, let's first check the mitigation status of WLAN to set up an exploitation strategy. From the table, we can see that the heap protections, heap ASLR, heap cookie, which makes the heap overflow issue pretty difficult to exploit. Okay. And there are stack cookie, and there are frame limit, and the return address protection. So we are unable to use the traditional ROP. ROP, you are unable to use it because protections. And also there are DEP. So we are unable to execute in the data segment. And also we are unable to write to the code segment directly. If we want to run arbitrary code, we should change the page attribution first. Okay. There are so many mitigations, but we are still very lucky. You can see the code ASLR is not enabled, and the global data data ASLR is not enabled. So the code is fixed in a fixed address, and the global data is in a fixed address. And CFI is also not enabled. So although we are unable to use the ROP, we can use something called function-oriented programming, that is FOP, to bypass the to do the job like the ROP, that is FOP. You will see later in the exploitation that all the gadgets in the FOP is constructed by a series of function calls. And also, we are quite lucky. The issue we found is in the global data area. Yes, the overflow we found is in the global data area. So there is no SLR, and we can overflow to a fixed address. Okay, let's check the vulnerability. The vulnerability CVE 2019-10540 already been announced in the Android and the Qualcomm August security briefing. Already been patched. If you are interested about the detailed information of the vulnerability, please check the security briefing in August 2019. This issue already have been fixed. Okay, this issue is in one of the offload handler. You know this table. It's in one of this table, and it's in the pre-auth frame handler. The pre-auth means you don't have to connect to a specified Wi-Fi point. You just turn on the Wi-Fi, you are leading to one level. Okay, pre-auth frame handler. Okay, I will translate it and simplify the assembler code into C code. So you can see here, this is a buffer. A global buffer has 10 items, and this is a loop which copy as much of data as possible into the global buffer. There is no check on the data count, and send 11 items will cause the global buffer overflow. This is quite straightforward, and okay. From the vulnerability code, we know that each loop it will copy OX44 bytes. Trigger the overflow, we can overwrite the content after this point, the global buffer plus B0, and into this the point will overflow into all this data segment. Okay, because there's no SLR, the address of the overflow data is fixed, so it's quite convenient for us to do the exploitation. Okay, and analyze the data near the overflow address, we can quickly find out that there is a very good data point at offset C. We overflow from here, and offset to C, there is a very good data point. We call it the smart pointer, which point to a very useful data. If we overwrite the smart pointer, we can do a lot of good job. Okay. Let's check the usage of the smart pointer. Okay. To better understanding the code, I will translate the code to C and simplify them at this figure. You can see this is the smart pointer. We can overwrite it. And this is the packet we send, the OTL packet we send through the Wi-Fi dongle. This is our data. We control this data. And this is the overflow data we control the smart pointer. There are two conditions, two tests. The first test is that we test the destination whether the noise bit is equal to 1. And the second test is that the smart pointer plus 6 equal to the MAC address of the sender. If both the tests pass, we can write to the 2 bytes, 3 bytes CD and 14 3 bytes. So, okay, let's see again. We overwrite this address, this smart pointer, and we do test. If the test pass, we write to the 3 points. Okay, so now we got an arbitrary write primitive with 2 constraints. The first constraint is the bit 0, and the second constraint is the MAC address. Although the MAC address is controlled by ourselves, so this is not, in fact, not a constraint. We can set our data send with the MAC address equal to this point. So the only constraint is this one. The lowest bit should equal to 1. Okay. If we pass this test, we can write 2 bytes or 3 bytes into the destination we are interested in. Okay. To summarize, I have drawn this picture. Okay. There are actually 2 steps. The first step, we will send a packet to trigger the overflow and overwrite the content of smart pointer to our destination we are interested in. And the second step, we will send another packet to use the new smart pointer to compare, and if pass, we will write something into the new destination. So now we can write 2 bytes using the vulnerability, 2 bytes, 2 arbitrary bytes. Okay. So another question is how a meaningful address or data is over 4 bytes. Now we can write 2 bytes. How to write 4 bytes? This figure shows the answer. Answer is quite simple, just using the write trace. The first time we write to the low 2 bytes, and the second time we write to the high 2 bytes. Okay, just move the smart pointer advance offset by 2, and you see we can write those whole 4 bytes. Okay, and there is another question. We have a constraint. The destination we want to write should have this bit set to 1. So how about if this bit is 0? The answer is that we could search up to check whether we can set this bit on. We search up and see, yes, this there is the 1, so we can write to this address, and then we write to the target we want to. Okay. So now we got a powerful global write primitive. Although we have the constraint, we should have a bit of value set to 1, but it is still very powerful. Let's see how we use the global write to control the PC and RVLO. The basic method is here. We search the full memory space and find out the meaningful place where satisfy the condition reachable by our remote packet, and that is interesting by us. For example, you can see here there is a PC and RVLO. If we could control overwrite this 4 bytes and overwrite this address, we can control the PC and RVLO. Okay, this is not very difficult to find a place similar to this table. You can see we have a lot of bit 0 equal to 1, so we can move the smart pointer down, move down, and finally we can write to this address using our arbitrary write. Okay. So now we have controlled the PC and RVLO. We can do some useful things. The first thing we want to do is to remove the constraint. That is, remove the condition. So we want to transform this global write to arbitrary write. Okay. The global write we have is still not very convenient, because the place we want to write should have the lowest bit set to 1. Generally, we'd better transform it to an arbitrary write. Okay, as we have controlled the PC and the RVLO, we can trigger some FOP to do the job. The FOP, function-oriented programming. Okay, we control the PC and RVLO. We set the RVLO to our payload, and then trigger this function and trigger this gadget. Finally, you will see that we have write arbitrary byte to arbitrary address. Okay. So we can do arbitrary write. We can run some other useful FOPs to do more complex job. To do the job, we have 3 steps. The first one, we overwrite one of the useful function pointer. Use the arbitrary write. The pointer should be able to trigger from the OTL packet. And the second one, we overwrite one of the parameter to generally R0. We overwrite the data pointer of R0. Okay, we change it to our payload, and the third step, we send the payload packet and trigger the function. Then our FOP gadget is running. For example, how we modify the attribution of the page. You know, we have DEP, so we have to modify the attribution of the memory page. So now we can run useful FOP to do the job. Okay. The function we're going to call is the create mapping function. It maps the arbitrary physical address to the virtual address we want and set the specified permission. Okay, for example, this address 936A is mapping to B00 with the permission Rx, that is read only and executable. It's in the code segment. So by triggering this function, we can map it to another address. Here we use 4242 to RWX, that is the full permission, read, write, and executable. So now we have a page that is RWX. Yeah, we can write to it and execute on this page. Okay. So another thing we want to do is to copy our shell code into the page. We just map out. We just want to copy the shell code to 4242. It's quite simple. We can do arbitrary write, and we have a page that is lots of choice. The thing I do is to overwrite one of the handler in the offload handler table, so that the R1 is originally set to the packet we send, and the data length is R2. So we overwrite the PC, the function pointer, and the data pointer. Then we can copy our shell code to the R0 we want to. That is the 4242 we just mapped out to be RWX. Okay. So we copy the shell code to 4242, we are able to trigger the shell code. So now we can running arbitrary code in WLAN firmware. Okay, just trigger the shell code in this address. Okay. Now we are in the WLAN. The next step is to escape into the modem. Okay. This is the load map, and we are now here. No, from here to here. Now we are here. We are going to the modem. Okay. The WLAN and the modem are in different processes in the baseband system. Okay, so here, this is the QERT OS kernel, and this is different processes. So how can we get into the modem? And there is actually some dangerous actions we can do. Just in this table, okay, some dangerous actions in the WLAN we can do. For example, we can try to write the modem memory directly in the WLAN. Also, we can try to call the modem functions. We can try, but it will fail. I think there may be some protections. I don't know why this is illegal. Okay, and also we are unable to modify the memory attribution of the modem using the TLB instruction. We are unable to do this. This will cause the modem crash. Okay, but finally we find out that we can map the memory of modem into WLAN directly. You know, the WLAN and the modem are in different virtual address space, but we can map the modem memory into WLAN. It's just like this figure. Originally, the modem physical address of modem is mapping to the virtual address of modem itself and WLAN to the WLAN itself. But now we can map the modem memory into WLAN address space directly, so that after we do the mapping, we can modify the memory space of modem to RWX in the WLAN, and so that we can change the code of modem, and obviously we can run arbitrary code in the WLAN or in the modem. So now we are getting into modem. Okay. So let's see how to escape into the Linux kernel from modem. Okay. So we are here. We are in the modem now, and we are going to here to the Linux kernel. The baseband subsystem is on a separated chip, not on the main chip that Linux kernel running. There are a lot of interface between baseband subsystem and the Linux kernel. Each of the interface is an attack surface. For example, there are many WLAN host issues in Android security bulletin every month. Most of them are firmware to Linux kernel vulnerabilities. These issues could be used to escape from the baseband into Linux kernel. And there are also partition attack surface from modem into high priority process, and also maybe into the trust zone. If you are interested, you can try. Okay. The vulnerability we are using is the CVE 2019-10538. Okay, in one of the attack surfaces. Okay. This issue already been fixed in the August Android security bulletin. And if you are interested about the detail, please check the August Android security bulletin. You can find the code diff. It's already public now. The code diff. You can check the code diff. Okay. It's just add some check for the incoming data packet from the modem in the kernel driver. Okay. There are some check if okay. Actually, it's about the memory management of the Qualcomm multiprocessor architecture. The memory management is quite a big topic, in fact. Here, you need to know that two things: the Linux master model, and the SMMU. The Linux master model means that the Linux decide the owner of the memory. For example, the Windows owns this memory. So how to get the memory by Windows? Actually, Linux will assign this memory to Windows. Before Linux assign it to Windows, Windows are unable to touch this memory. Okay. So after Linux have assigned the memory to Windows, the SMMU will protect it to protect it, and if the modem or other subsystem wanted to access into this memory, the whole system will crash. That is the SMMU doing. It protects the memory to make sure the memory assignment by Linux work as expected. Okay. So another example for this memory is owned by the modem. So Windows and Linux, they are unable to touch this memory. Okay, but the job is done by the Linux. Linux will decide the address and the owner of this memory. Okay. This is Linux master model and the SMMU protection. Okay. So the issue here, 103.105.38 is here in the memory management. There is actually a mystery logic. Generally, Linux itself will decide the address and the size to assign to other peripheral subsystem. But here you can see the modem have send an address and the size to Linux, and then Linux will assign it to modem directly without any check. I don't know why this address is decided by the modem. In Linux master model, it should be decided by the Linux itself. But here, this mystery code seems very wonderful for us to exploit, because we can map any physical memory designed by us. Because we have to control the modem, we can use any physical memory. We can here tell the Linux, we want this memory, then the Linux will assign this memory to us, so we can own this memory. If we tell the Linux to give the code of Linux kernel to us, it will do as we want. So this is the vulnerability. We tell the Linux that we want the code space of Linux, so Linux give to us, and so that we can modify the content of the kernel code. So we have an arbitrary memory right of the Linux kernel. That's the vulnerability. Okay, please note that this vulnerability is pretty powerful. We just bypass any modifications in the kernel, because we are using the physical memory. That we just assign the physical memory, and we can bypass the KSLR and other modifications. Anything is useless. Okay. So we have break into the kernel. But before we watch the demo, I would like to talk a little more about the stability of the exploitation, because we are sending the packet over the air. It's the wireless packet. Okay, there are some stability issues. When I do the test, I'm using a Wi-Fi dongle, just like this one, and the SCSI software to send out the payload here. But when I do the test, the packet losing rate is very high, almost 90% of payload are lost. That's make our exploitation very unstable and will crash every time. We are unable to complete the whole exploitation chain. Okay, but the reason why losing packet is quite complex for me. Finally, I have found the solution. I have a Google Pixel 2 with Snapdragon inside, which could send and receive packets normally. Surely the Pixel 2 could solve the problem I encounter and send the packet correctly. So how about we use the function that the Pixel 2 is using to send out the packet? Okay, we can hook the function in the firmware which send the specified packet we want on Pixel 2. We replace the content of the packet to our attack payload. Okay, that is the solution. Finally, we are using the Pixel 2 to attack the Pixel 2 XL. Yeah, we send out our payload using the Pixel 2, and the target is the Pixel 2 XL. And, maybe you ask how we hook the function in the firmware. It's another complex story. Actually, we don't have enough time to talk about it today. Okay. Finally, we are here. we using a Pixel 2 into the WLAN and into modem and into Linux kernel. This is the full exploit chain. Okay. Let's watch the demo. Okay. I don't know how to play it. Okay.
Yes.
Okay. Directly play it. Can you see? Okay. Okay. Let's explain something before we go. This is the Pixel 2. You can see, well, this is the attacker. This is the phone we have compromised, we own. And this is the target, the Timen, the Pixel 2 XL. Okay. Now we are going to send a packet. We prepare the attack on the Pixel 2. Yeah, you can see, explore start. We are send out the packet. Okay. The first payload is 143 lanes. Okay, that still send the packet. The Pixel 2 XL is G86. Okay, you can see that the SE Linux is enforcing, and we are unable to use the demessage from on the shell. We are in the shell. Okay. So the Pixel 2 is sending packets. Okay. We can the whole process needs about three minutes, but we don't think we have to wait. Let's speed up. Okay. Okay. Attack is not finished. You can see the SE Linux is still enforcing. Okay. Okay. To speed up about 3 minutes. Okay. Okay. The portion done at this time. Okay. Let's check the result. Okay. Just wait for minutes. Okay, you can see it's permissive. So we have fully controlled the Linux kernel and set the SE Linux to permissive. Okay. We are still in the shell, but we have controlled the Linux kernel. Okay. Now we can visit the demessage, print out the kernel message. Okay. Okay. This is the demo. Thank you. Okay. Okay, and the future works, there are still lots of mystery in WLAN. So we just reverse engineer a small part of the code. Lots of the functions of the WLAN are unknown. And how to fire the WLAN firmware and how to transfer the instruction to C, maybe. This is the timeline. We report the first issue on February the 14th, and Qualcomm and Google responds very quickly. And now these issues have already been fixed in the August security briefing. Okay. And this is our talk. You just remember this figure. We from WLAN to modem and to Linux kernel. And also we talk about how to hunt vulnerabilities in the WLAN. Okay, you remember the data pointer. The data pointer we are using. Okay. Also, we know how to debug the baseband. If you want to future research, you can use the debugger. Okay. Okay, that's all. Thank you.